Okay, we're going to cover equipment operation and quality assurance. So we're going to talk about the tube and fluoro. So here are the different areas, the components of the radiographic unit. So we're going to talk about fixed and mobile. We're going to talk about the operating console, the tube construction, AEC, manual exposure control, beam restriction, generators, and rectification, and we've got fluoro. So the components of digital imaging and accessories will be in another video. So 4 and 5 are in a separate video. All right, so let's get crack-a-lackin'. So we got number 1, components of the radiographic unit, so fixed and mobile. So let's start with our operating control system, right? So it allows us as technologists to control the X-ray tube current and voltage. So the tube current normally is between 100 and 1200 mA, and the voltage is 25 to 150 kVp, right? So ensures the useful X-ray beam is of proper quantity and quality. So as you can remember, X-ray intensity is our quantity, where the penetrability, so when we say that, we're talking about the penetrability of the beam or the quality of the beam, right? So that is our kVp, okay? So quantity versus quality. So quantity, the intensity, refers to the number of X-rays in the X-ray beam expressed in milligrays or milligrays amperes per second, which is MAS, right? Where our quality is our penetration. It refers to the energy of the X-ray beam expressed in kVp, or to be more exact, it's expressed in half value layer. Operating console provides control over line compensation. So you don't have a lot of control over that, but line compensation, kVp, MA, and time. So the electric circuit operates at a low voltage to protect you so you don't get shocked on the high voltage side. So the operating console is low voltage. Let's talk about tube construction. We have the cathode, the anode, and the electromagnetic induction motor. So the cathode is the negative side of the tube, consists of 2 parts. There's the filament and the focusing cups. So as you can see, here's the filaments, and you've got your focusing cups surrounding it. The filament is made of thoriated tungsten due to its high melting point. So 1 to 2% of thorium has been added to the cathode, to the filament, to help with the vaporization, right? So vaporization is the most common cause of tube failure. So the filament circuit heats up to over 2200 degrees Celsius, 3 to 5 amps to cause emissions of electrons, okay? So it heats up really hot to boil off those electrons through thermionic emissions. So the focusing cup, it's negatively charged so that it electrostatically confines the electron beams to a small area on the anode. So it keeps all those electrons from running free in the playground. Remember how we have the fence? So effectiveness is determined by the size and the shape, the charge on it, the filament size and the shape, and the position of the filaments. Okay, so here is our focusing cup, and you can see our filaments in there. We have a small and a large, and you can see if we don't have a focusing cup, this is just the beam. So the electrons like to spread out away from each other because they're both negative. All of them are negative, so they're trying to get away from each other, repel each other. With the focusing cup, we can get them into a stream. Okay. So dual focusing cup is most common. It means it has 2 filaments, allows for small and large. Small is better resolution, where the large has not as good of resolution, but it can handle more heat, okay? So let's talk about the anode. There's 3 parts: the anode, stator, rotor. It's the positive side of the X-ray tube. There's 2 types of anodes. They're stationary and rotating. It serves 3 functions. It has mechanical support for the target. It is an electrical conductor, which means it receives electrons emitted by the cathode and conducts them through the tube to the connecting tables and back to the high voltage generator. Okay, so it's considered an electrical conduction. It's also a thermal dissipator. So 99% of the heat is heat when the electrons bombard the target, right? They're typically made of copper, molybdenum, and graphite. Those are the most common. So copper is typically the stem, molybdenum is the base that the track is on, and graphite is a piece usually on the back of the base to help with dissipating heat. So the target is the portion of the anode where the high voltage electron streams hit, right? It can be called the target of focus, the focal point, and the focal spot. Now, typically we call it a focus track, right? Focal track. So it's continuous, represents a circular path that will be impacted by electron beam in a rotating anode. Whew, hard for me to say. So stationary, this is what they look like. It's just got a copper base and it's got the tungsten target right there. It's at an angle. And the tungsten is embedded in the copper, so there's less surface area for the electrons to hit as the target. It's less heat tolerant, therefore not capable of doing high intensity X-rays. And usually these are used in dental. We used to use them in mammo until recently. So rotating anode, allows electrons to interact with a large target area, approximately 500 times more than the stationary. It allows for higher tube currents and shorter exposures, which is great. Target is coated with tungsten, right? So molybdenum and graphite base is typical and operates through electromagnetic induction. So the speeds are anywhere from, depends on your textbook, it could be 32 to 3400, right? Depending. So typically it's 3,400 to 10,000. 10,000 is the high capacity tubes, so they can handle a lot more, okay? So tungsten is the target material choice for 3 reasons. Remember, high atomic number, so it's great and high efficiency X-ray production, okay? Thermal conductivity, it's similar to copper, therefore efficient metal for dissipating heat. And high melting points, so 3,400 degrees Celsius therefore can stand up to high tube current without pitting or bubbling or causing tube failure is what we say. So the focal spot, so if we look, the focal spot is the actual X-ray source. So actual focal spot describes the physical area of the anode track that is impacted. So here you have it coming across from the cathode, it's being hit. So this is your actual focal spot coming off right here with the angle, okay? Your effective is what comes below. It describes the area of the focal spot that is projected out of the tube towards the object being radiographed. So I think of it as the effective is what is effective in giving us our X-rays, right? So the effective comes out of the tube and hits the patient. That is the effective beam, right? So easier to remember. So as the actual focal spot increases, the effective focal spot increases. So as this gets bigger or smaller, so here small going big, you can see that the effective is getting larger. So the line focus principle. So used to reduce the effective area of the focal spot so that you can get the best resolution, okay? The principle was created before rotating anodes were developed as a way to heat up a large area while maintaining a small focal spot for detail, okay? The effective focal spot is controlled by the size and the actual focal spot and the target angle. So we've talked about this before. So the effective focal spot size decreases with decreasing target angle. So if you have a 24 degree versus a 12 degree. So as we take this and make this straighter, you can see how much straighter it is. It's closer to 0, right? So as the angle decreases, so does your effective focal spot. As your angle increases, so does your effective focal spot. Okay, do you see how that is? I worded it the same, but opposite. Okay, so smaller target angle, smaller focal spot. The main advantage improves resolution and heat capacity, and most X-ray tubes have a target angle between 5 and 20 degrees. That's important. Anode hill effect caused by the angle of the anode. The smaller the anode angle, the larger the hill effect. So X-ray intensity is lower on the anode side because the X-rays have longer path to make it through the target material, results in absorption. So those metals are absorbing your photons, okay? The difference in radiation intensity across the useful beam can be up to 45%. It's huge. Remember, fat cat, fat cat, fat cat. So position the cathode side of the tube over the thicker portion of the anatomy, and it gives you a more uniform optical density. As we can see here, we've got the metal is absorbing our photons, so we have less intensity compared to the cathode side. So the Hill effect is important when one is imaging anatomical structures that differ greatly in thickness and mass. So the abdomen, the chest, mammo, feet are a big one. The effective focal spot is smaller on the anode side of the X-ray beam. or the field than the cathode side. So fat cat, just remember that. It's going to be more intense on the cathode side. Let's talk about off-focus radiation. Now, it's X-rays produced on the anode other than the focal track, okay? Produced from rebounding electrons. Undesirable because it extends the size of the focal spot, results in reduced image contrast. So what it's doing is putting scatter radiation on your IR, okay? Fixed diagrams that are placed in the window of the X-ray tube were created to reduce extrafocal radiation. So that's what we call extrafocal radiation. So electromagnetic induction motor. So let's talk about the rotor and the stator. So the induction motor works by electromagnetic induction. The stators are located outside. So that's going to be a test question on your exam. The stators are outside, the rotors on the inside of the glass envelope. They do not touch each other. They spin through electromagnetic induction, okay? All right. So let's talk about tube failure. Pitting and cracking. This happens from a single excessive exposure. Bearing damage, so multiple long exposures, so you're exposing a T-spine over and over and over, and that will wear out your bearings. They warp a little bit, and then your anode is shot. So filament vaporization, we've talked a lot about that. That is your tungsten vaporization. It may vaporize so much that your filament may break, right? And it also coats the inside of your tube. Okay, and then when you hit expose, it'll arc over to the tube instead of to the anode. Okay, so tungsten vaporization is the most common cause of tube failure. Don't get that wrong. All right, so let's take a look. This is a new anode. Look how shiny and pretty. So we go here. This is just overloading of the anode. This is pitting. This is normal wear. Okay, we see this a lot. This is pitting, normal. Wear and tear on your tube. Eventually it will fail. Okay. So here, this is excessive, exceeding maximum heat storage capacity, resulting in melting. So you can see where it's melted. Now, I may even call this bearing failure. As you can see, it's like stuttering instead of being a continuous beam of electrons. And then we have D, which is heat damage of the rotor bearings from overloading. So there you go. Too hot. All right. Tube fail prevention, really important. Tube life can be extended by using minimum MA, KVP, and times. And make sure you use what's appropriate for the exams. Don't extend them. Don't go higher than you should. You should always warm up your tubes, okay? Maximum radiographic techniques should never be applied on a cold anode. And do not allow exposures at or above the tube limits. So the good news is your tubes will make you warm them up if you haven't done it in a while, and they will not allow you to expose over what is allowed. Now, if you're on a really old unit, they will. So you need to make sure you warm them up and that you do not exceed your exposures. All right, automatic exposure control. So we have radiation detectors with a backup timer and exposure adjustments. So we can go +1, +2, +3, or -1, -2, -3, right? And it gives us the minimum response time. So AEC measures the quantity, not the quality, the quantity of radiation reaching the image receptor. And it's usually the time that is being adjusted, okay? The MA is set. So exposure automatically terminates when sufficient radiation has reached the IR. Ionization chambers is the most common, okay, that manufacturers incorporate. So we have photomultiplier tubes. So they phosphorescent screens convert light produced by the screens to electric charge and terminates when a pre-selected charge is reached. So this is kind of older school, but that's okay. Ionization chambers always ionize the cell, and when preset ionization levels are reached, exposure terminates. All right, so manual exposure controls. So as an X-ray, controls shall be incorporated into each X-ray system, which allows the operator to terminate an exposure at any time except for one or more of the following. So exposures of ½ second or less, or during a series of radiography in which the case a means shall be provided to permit completion of a single exposure of the series in process. Okay, beam restriction. So light field to radiation field alignment. You need to make sure that those align, right? So we talked about that in our QA. You'll have videos on it later. So central ray alignment. So what it is the light that is shining should represent the X-ray field, okay? And that's how you're going to center, as we know. All right, so back to generators, transformers, and rectification. Okay, here we go. This is back from long ago. So X-ray systems, we have an operating console, we have the high voltage generator, and we have an X-ray tube, right? So we're looking at KVP control, we're looking at MA and time selections, we have a step-up transformer, we have a rectification circuit, we also have an X-ray tube with the filament circuit. So let's talk about them. We have here our control console right here. We have our high voltage section, our X-ray tube. So in our control console, we have our incoming line current, right? We have a timer, our line monitor to make sure that the incoming line current is where it needs to be. We have an auto transformer. Off the auto transformer, we have our KVP selector. Then we have our major and our minor with the KVP meter, making sure that it's where it's supposed to be. And we have our timing circuit and selector. Then we go into, this is all low voltage, right? Low voltage. So here coming across, we have a step-up transformer with rectifications with the MA meter and rectifiers, and that goes to our tube. So on our filament circuit down here, we have our MA selector, which we call a rheostat. Remember that? Rheostat. We have a step-down transformer right here. Okay, so what is happening in the step-up and step-down transformers? Here in this one, we have a step-up transformer. We're taking our KVP and we're stepping it up and we're reducing our MA. Okay, we need to get it from volts to kilovolts, and we do that by dropping our MA. Coming down here in the step down, we're dropping our voltage and we're increasing our MA, okay, to amps, from milliamps to amps. All right, so the operating console allows the RT to control the X-ray tube current and voltage, provides a control line compensator, KVP, MA, and exposure time. So there's meters that monitor the KVP, MA, and time, and some have mass meters. It just depends. So if we look here, we went through this, so we have our line compensator with our auto transformer coming all the way down. We have our minor and major KVP selectors with our timer and our circuit timer. So here we have our MA selector, which is our rheostat, and it goes down, they move forward from there. Okay, so this is how we're selecting our KVP and our MA is off of this portion. Sometimes we can do from the tube, which is really cool. Okay, the line voltage compensator compensates the incoming voltage so it is constant voltage may be used during the exposure and not varying the voltage. So it corrects the variations in power coming in from the wall here. Okay, so here's our line monitor, here's our auto transformer, and we got a line compensator, switch, and meter. So it's going to flip around and make sure that we stay consistent. The auto transformer, the first part of the system to receive the power, supplies the voltage, both the filament and the high voltage circuit of the system, has one winding and one core with a number of connections. It has primary and secondary connections for increase and decrease of input voltage. All right, so the auto transformer law uses the auto transformer law, which is the same as a transformer law. So voltage secondary or voltage primary is equal to number of windings secondary to number of windings primary. Okay, so KVP control determines the quality or the penetrability of the beam. So there's minor and major. So here we got the major and the minor. A combination of major and minor KVP gives the appropriate KVP readout for the exposure. There's a KVP meter that reads the voltage, not the kilovoltage. So it's a pre-read of your KVP meter. Okay. X-ray tube, so this is our MA control. X-ray tube current is measured in MA. It controls the number of electrons crossing from cathode to anode. As temperature increases, more electrons are released via thermionic emissions. Space charge effect is eliminated by a correction circuit, and X-ray tube current is controlled through a separate circuit called the filament circuit. So the filament circuit. So if we take a look here, we've got an auto transformer. So this controls the X-ray tube current. Okay, it receives the voltage from the auto transformer, and precision resistors ensure the voltage received corresponds to the MA selected. So here we're coming in and we're doing a step down transformer. Okay. Falling load generator. So this is a certain kind, okay? Exposure begins at max MA and drops as the anode heats. Results in minimum exposure time, causes kVp to fluctuate throughout the exposure, and can shorten tube life with the consistent use of the high MA. Let's talk about the MA meter, okay? Monitors the X-ray tube current. Connects to the center of the secondary side of the high voltage step-up transformer. The secondary voltage alternates at 60 Hertz. No part of the meter is in contact with the high voltage. So the filament transformer. It has an MA selector, so right here. The focal spot selector over here, and a step down transformer right here. Exposure times, separate from other main circuits, has a device that works to make and break high voltage across the X-ray tube, usually on the primary side of the high voltage transformer. Types of timing circuits. So there's synchronous, electronic, mass, and AEC, right? Automatic exposure control. Let's talk about timers here. So driven by a synchronous motor, which operates at 60 revolutions per second. So these synchronous timers are recognizable because the exposure times are in intervals of 60. So 1/60th, 1/20th, 30th. So have to be reset after each exposure. The most expensive is our electronic timers. They're the most complicated, most accurate of X-ray timers. Composed of complex circuitry, allow for a wide range of intervals to be selected, and accurate to intervals as small as 1 millisecond, and can be used to make series of exposures, which is nice. So electronic timers are what we use today. There's mass timers. So it's a type of electronic timer located on the secondary side of the high voltage transformer. Monitors the product of MA and exposure time and terminates exposure when the desired MAS is reached. Usually set to give the highest MA with the shortest time. So automatic exposure control measures the quantity of radiation reaching the IR. Exposure automatically terminates when sufficient radiation has reached. Ionization chamber is the most common. Okay. So there's a high voltage generator, converts low voltage supplied from the power company into high kilovoltage required to produce X-rays, and high amperage to the milliamperage needed to produce current to the filament. There are three parts. There's the high voltage transformer, there's the filament transformer, and there's rectifiers and diodes. Okay, so high voltage transformers. There's the step-up transformer. So due to the number of turns, the secondary voltage is higher than the primary side. So you can see we've got a big step up right there, and only operates on alternating current. So voltage rectification is the process of converting AC to DC, okay, for the X-ray tube. Ensures electron flow in one direction from cathode to the anode. So any changes will cause rupture of the tube. So vacuum tube rectifier. So for the cathode is negative end, contains a coil of wires that is heated so that it releases electrons through thermionic emissions, where the anode is positive end, attracts electrons, so the electrons flow from negative to positive. Now if we have an unrectified current, right, it would look like this. So we come down and up and down and up, and we have a negative side. So we have positive and a negative. We can't have that, right? So this is an unrectified voltage. So rectification is essential for the safe and efficient operation of the X-ray tube. This voltage waveform appears as a voltage waveform supplied from the primary side of the high voltage transformer, except its amplitude is much greater, okay? So half-wave rectification. So a condition in which the voltage is not allowed to swing negative during the negative half of its cycle. So the rectifiers convert the alternating current to direct current to operate the X-ray tube. So the positive portion of the waveform allows the electric current to pass through the tube. the negative portion of the waveform, rectifier does not operate, no current is allowed. The result is a series of positive pulses separated by gaps where negative current is not conducted. Okay, so what we do is we just take it here. We have our pulse. This would normally come down here, but we just took it and flatlined it. Okay, and flatlined it. So contains 0, 1, or 2 diodes, produces 60 X-ray pulses per second. Disadvantage, we waste half the power supply and requires twice the exposure that we normally would use. Now if we do full wave rectification, that's 4 diodes, the negative half of the cycle is reversed. So we take it and we flip it up, okay, so that it is always positive. Exposure time for any given technique is cut in half, so it produces 120 X-ray pulses per second. So nice. So as you can see here, this is a normal sine wave right there, and then we have rectified. This is with 2, so we're just flatlining right here. We're just turning this off, okay, so the negative portion. Then we use 4 diodes here, and we've got a positive only, so we've cut out the negative side, so we have direct current, and you can see that it makes a big difference there. So we've reduced our time by half, our exposure times. So single phase power results in pulsating X-ray beam. Voltage alternates from 0 to a maximum potential of 120 times under each second under full wave. So X-rays produced when the waveform is near 0 or of little diagnostic value. In order to compensate for this rise and fall, we went to 3-phase power. So 3 waveforms are provided so that the resulting waveform maintains nearly a consistent high voltage, never dropping to 0 during the exposure. There are 6 pulses per 1/60th of a second compared to 2 pulses in single phase power. Limitations to the speed of starting an exposure, which is initiation time, and limitations to ending an exposure, extinction time. Is the principal disadvantage is the cost. So we have single phase, we have 3-phase. So you can see 3-phase, we have 3 different ones going at the same time. And then we go to 6, we have 6 different ones going at the same time. So as you can see, the voltage drop, this is 100% voltage drop. We go from high to 0, 100%. Here we have voltage drop, but not as much. And here we have less voltage drop, which is good. High frequency is what we want to use though. It's the most efficient of all generators, produces nearly consistent electrical voltage waveform, providing image quality at lower patient dose. It is used 500 to 25,000 pulses per second, used in most modern X-ray systems and mammo units. Okay, so you can look here, you can see the variations. So half wave, 100%, full wave, 100%. We go to 3-phase 6 pulse, we're at 14. 3-phase 12 pulse, we're at 4, so that's pretty good. And we got high frequency, which is less than 1%, which is fantastic. You don't want any fluctuation. All right, so this is saying the same thing. Tube rating charts. There are 3 types of charts that are available to help us to keep us from blowing the tube, right? So there's radiographic tube rating charts. So the charts techniques that are safe and unsafe for X-ray operation. There's anode cooling charts, the time required for the heat anode to cool, and there's housing cooling charts. The time required for the housing of the X-ray tube to cool. So the tube rating charts are the most common, and this is what you're going to see here. The biggest thing is make sure you get the proper graph. So we look here and we say, okay, we're at 3,400 RPM. This is 10,000 RPM. This is single phase 6 millimeter, 11 degree, 3-phase 6 millimeter, 11 degree. Or you can go, this is 3,400 single phased 1 millimeter at 11. So these are the same except for the focal spot size. Okay, these are the same except for the speed. So always make sure you get the right graph. And then what you want to look at is it is safe under the line. So if you're at 125 kVp at a 0.1 here for your exposure time, you're fine. Okay, so all these graphs are the same. Just make sure you pick the right graph because they're going to give you a few of them. They're going to ask you, is this time in kVp safe with the MA? So you find the MA, so it's 500 at 1 second and it's 125 kVp. Is it safe? It is. Here's 500. Here's 0.1 second, it's safe, but at 1 second it's not. It's above the line. Okay, so anything below this line is safe. Okay, that's how you read them. Super easy. Don't make it harder than what it is. All right, let's jump into floral. So, allows imaging of the movement of internal structures, is a continuous beam of X-rays to create images of moving internal structures, uses a really low MA of 0.5 to 5. It has a dead man switch, so if you let go of the switch, it stops exposing. And it's required to have a 5-minute timer on it, an audible timer, okay? Fluoroscopic images are viewed on a monitor. So the image intensifier provides a method of increasing the brightness of the fluoroscopic image to improve its viewing. So the input phosphor converts exit radiation to visible light. The photocathode converts visible light to electrons. Electrostatic lenses accelerate the electrons towards an anode to strike the output phosphor. The output phosphor converts the electrons to visible light. So brightness gain, you have the components of flex gain and magnification gain. Okay, so those, make sure you know what those are. The flex gain is how much you gain. The magnification gain is how much has been magnified. Okay, so conversion factor, so equal to the amount 1% of the brightness gain. Okay, the greater the conversion factor or brightness gain, the greater the efficiency of the image intensifier. Okay. So if we look at these image intensified fluoro, so if we take a look here, we've got under the table, we're coming up, we have our input phosphor, our photocathode, we've got our electrostatic lenses with our focal point, and we've got our anode right here and our output phosphor right there, okay? So here's our light photons that will come up onto a monitor, okay? So here we have our input phosphor, and we've got our photocathode, our electron stream with our electrostatic lenses, with our focal point, with our anode, and our output phosphor. So ABC, automatic brightness control, maintains the overall appearance of the fluoroscopic image. So contrast and brightness by automatically adjusting the kilovolts and the MA or both, okay? The fluoroscopic unit allows the operator to select a desired brightness level, and this level is subsequently maintained by the ABC. Mag mode, okay. Magnification mode improves visibility of small anatomical structures, okay. Voltage through the electrostatic lenses is increased. The focal point right here is shifted further away from the anode, okay. So operating in mag mode will increase patient exposure, okay, so it does kick up the exposure. The viewing system, so we have closed circuit television monitor, we have visible light from the output phosphorus converted to an electronic video signal, there's camera tubes, there's charge coupled devices. The difference between the camera tube and the CCD is the size and the readout process. There's CRT television monitors. It includes electron gun receiving the video signal that can scan the phosphor layer inside the glass front. There's liquid crystal display, so LCD monitors. Contain several layers, including liquid crystal layers sandwiched between polarizing layers. And plasma monitors, similar to LCD monitors, but replace the liquid crystal layer with a layer of pixels that contain 3 neon and xenon gas-filled cells. So typically we see these liquid LCDs and with the plasma monitors are what we're seeing today. Okay. Recording system. So one way we used to do it was cassette spot filming. It's a static image process using radiographic cassette. Okay, so pretty old school, right? The MA is increased from one of the 0.5 to 5 MA fluoroscopic modes, and one of 100 to 1200 MA radiographic modes. Okay, so it takes the MA and jumps it way up. Okay, so from the fluoroscopic 0.5 to 5 all the way up to 100 to 1200. So it takes the machine a second to do that. Okay, when you do this, you're increasing your patient exposure by a lot. Okay, there's photo spot cameras and there's videotaping, DVD recording also. So as you can see here, here's our mobile C-arm. So we have our input, our photocathode, we have our electrostatic lenses, we have our anode, we have our focal point. Coming through, you can see the spot film right here. It's got a mirror, and we've got our television where it comes up and we can see it on the monitor. But we have to convert it from analog to a video to digital, and then to our digital image. Okay. It's a lot to it. So digital floral, analog to digital converters, right? So we need the ADC placed between the television camera and the monitor. Flat panel detectors are more recent advancements, replaces the image intensifier, which is really cool, operates at higher MA similar to radiograph. Okay, X-ray beam is automatically pulsed to reduce the heat loading. So that is different compared to an II, right? The image intensifier. This, with digital fluoro, it's pulsed all the time. So continuous fluoro, X-ray exposures continuous without interruption. It increases patient dose. And then we have pulse fluoro. An exposure is not continuous and has gaps between the exposure. And when we do this, it decreases the dose, okay? So A is continuous fluoro, produces 30 frames per second during a period of 1 second, where before, when we're dealing with IIs, it was just on all the time. It didn't have this pulse feature, okay? When we go to B, the pulse fluoro can vary in the number of images or frames per second. This has a sample of 7 frames per second. 1, 2, 3, 4, 5, 6, 7. 7 frames per second. All right, so intermediately pulsing the continuous X-ray beam will reduce patient dose. Operating the fluoroscopic in the lowest pulse mode with the lower dose with minimum patient exposure. Time distance shielding is always used. The intensity of the X-ray exposure at the tabletop should not exceed 10 R per minute. For equipment with ABC or ABS, and 5 R per minute without ABS, okay? The source to skin should not be less than 38 centimeters or 15 inches for stationary fluoro units and not less than 12 inches for mobile units. But California says you should be at 18, right? All right, shielding. Shielding is recommended at 5 millimeters of lead equivalent. The Bucky slot covers and any protective curtains or gloves or anything should be at 0.25 millimeters of lead. Okay. So the components of digital imaging, number 4, is going to be recorded separately along with the accessories. So that is your review for today.